after thinking about control systems in general in somewhat descriptive terms, we will turn our attention now to something more specific. We'll soon start writing down equations and things like that. So I'll start with an example. Of course, it will be a classroom example. So one may not expect to find the control system about which I will start talking in some place exactly the way I am telling you. But the purpose of the example is to convey some of the concepts and ideas that are involved in the study, analysis and design of control systems. So keep that in mind. Also, you will have to read up about some of the things that I mentioned from a good textbook. I am assuming that most of you are familiar with electric motors of various kinds. In particular, we will take up a simple electric motor, namely a DC motor. Now, a DC motor, as you know, has two windings. One winding is called the armature winding and the other is called the field winding. The current in the field winding produces the magnetic field, and the conductors which constitute the armature winding, when they carry a current, interact with the magnetic field, producing a force or a torque, and that's how the motor rotates. Of course, as you know, because I'm talking about a DC motor, what is called a commutator is required. Now, the motor, for our purposes, will start drawing diagrams, will be represented by a more or less standard symbol. Do you recall the symbol for the motor armature? Well, it's something quite simple, and it suggests the shape of the armature as well as the fact that rotation is involved. So here is the symbol for the motor armature, and two little things are placed at two ends of a diameter, and these are supposed to represent the brushes that press upon the commutator. So here are the two wires that are connected to the brushes so that armature current can be made to flow. Remember this symbol of a motor armature with a pair of brushes. Since it's called an armature, we'll denote the current in it at any moment of time by the standard symbol for current, which is I, with a subscript A to remind us of armature. And because the current may be changing with time, I'm showing it as IA as a function of time. So far I only have the armature of the motor, but as I mentioned earlier, there is another winding which produces the magnetic field, and this is shown by a symbol which normally represents an inductor or a coil. So here is the symbol for the field winding. The coil is supposed to remind you of a magnetic field, and indeed wire is wound around the pole area of the which results in the production of the magnetic field. This winding will also carry a current because it is the field winding. The current flowing in it at any moment of time, we'll denote it by I again for current in general, but F for field current, and if it is varying with time, then T. So IF of T will be the field current, IA of T will be the armature current at any moment of time. Now, what is the purpose of using the motor? The purpose of using a motor obviously is to make something else turn, go at a certain speed against a resistance, a mechanical resistance. In other words, the purpose of the motor is to generate a torque. There is no fairly standard symbol for torque, but again one can use the letter T to remind us of torque. The torque may also vary from time to time, and of course one may put the letter M to remind you of the motor. So this is the torque which is produced as a result of the interaction between the armature current and the field or the flux, magnetic flux, which is produced by the field current. One may have to talk about the flux that the field current produces in what is called the air gap of the machine near the pole area, and for that the standard symbol usually is capital Phi, and if it is varying with time, then of course phi shown as a function of time. So phi will denote the magnetic flux in the air gap, and the way in which we think about it is that the field current gives rise, that is the flow of the current in the winding produces magnetic flux phi in the air gap, passing of course through the core of the armature. The armature is also made of magnetic material, and thus there is a possibility of an interaction between the armature current which flows in the conductor and the flux in the air gap, as it is called. The motor, as I said, is going to drive something, is going to make something turn, and because it's motion, it will be some mechanical device. For example, the motor could drive, or on the shaft of the motor may be mounted a grinding wheel which is used for grinding, or it could drive the shaft of a lathe, and the lathe in turn may be used for some machining operation such as simply turning or screw thread cutting and so on. So we show this again on the diagram by showing what looks like a shaft going from the armature, or the armature shaft and the shaft of the device which is being driven, and I'll show it here simply as what looks like a disc or a pulley. And to indicate to us that the shaft is rotating, one puts an arrow around it this way. Now the shaft will be turning, and so we need a symbol for the angular velocity or angular speed of the shaft. For this, normally the Greek letter omega is used, and the speed may change with time, so we'll call it omega t. I have shown the motor driving the load directly, that is, the load is directly coupled to the motor. This may not be the case. There may be a gear train involved between the motor shaft and the load shaft, and so we may have to distinguish two different speeds: the speed of the motor, which may be different from the speed of the load. We can think of the load as something which has to be rotated, and that requires some torque to be applied to the shaft. So this torque is referred to as the load torque. So for the symbol we will have T, capital T with subscript small l. That's the load torque. What's the difference between the torque produced by the motor Tm and the load torque TL? There may not be much of a difference for the figure that I have shown, where the armature shaft is directly driving the load, but as I said, if there is a gear train in between, then the two torques will not be equal because the two angular speeds are not equal. Moreover, there may be some friction in the shaft at various bearings. As a result, not all the torque which is produced by the motor will be used in driving the load. So Tm may not be equal to TL, and if I want to distinguish between the motor speed, angular speed, and the load angular speed, I may of course do it with subscripts omega m T for the motor speed and omega L T for the load speed. Diagrams like this are extremely important, as you know. In fact, this is what makes one a good engineer. If you are able to put down, with the help of the standard symbols, whatever you are thinking of or whatever you are talking about, and similarly if you can understand a diagram such as this one, because this diagram is still not complete and we will complete it. Such a diagram is known as a schematic diagram. In fact, there is a redundancy of words because the word schema in Greek itself means a figure, but this expression is very commonly used. So what I have started drawing is a schematic diagram of what may be called a drive, a mechanical load driven by an electric motor. Now, what is the control system here? Strictly speaking, we should, and I have done that earlier also, we should distinguish the two parts of the thing that you see here. One is the load in this case, and the whole purpose of what we are doing is to make that load, maybe that pulley or whatever disc, grinding wheel, to turn against a mechanical resistance. So that's what is the purpose of the whole thing. That's why it's called a drive. Now, of course, there are various ways of trying to meet that purpose. For example, a very crude way would be to put a handle at the end of the shaft and to turn the handle by hand, that is, crank the handle manually. But of course, one will not do it normally because the speed will be very low, the torque that a human being can apply will be also not enough. So in other words, you go beyond some simple solution like this, and let's say by the time you are thinking about this problem, the electric motor has been invented. So you say, all right, somebody tells me that there is this thing called an electric motor which can do this job of driving the grinding wheel. It can drive it at a sufficiently high speed. As you know, grinding requires quite high speeds, and also it requires a high torque. So one has decided that the load will be driven by an electric motor. The electric motor can be said to be, in this case, the prime mover, or in other contexts it is called an actuator. And now the shaft of the load, because it is connected to the shaft of the motor, we are no longer going to crank it by hand. So whatever we want to do to the grinding wheel or to the mechanical load will be done through the agency of the motor. So the motor becomes the controlling system, the system that ultimately controls the load, what happens to the load. But the motor in turn needs to be controlled. Now before we go into that, I said the motor, I didn't say what kind of motor. So there are of course various kinds of electric motors. One obvious classification is into DC motors and AC motors. Nowadays you don't find a DC supply coming to your house or even to your industrial establishment. What you have provided by the supply company is AC alternating voltage and current. That too may be of a voltage level which is not what an electric motor that you are thinking of may be using. So one has to make a choice: shall I use an AC motor which will run directly on what is provided to me, or that may be expensive. I may therefore use a transformer to step down the AC voltage to a level such as say 230 volts RMS, and then use an AC motor which will run on that lower voltage. One has to make a choice. Now from a practical point of view, such a choice is very important, because ultimately you have to put something there. You can't say do anything, put something. You have to know what you are going to put. Now such choices are rather difficult to make and to put down in a course. Such choices require experience. So we are not going to look at such choices. Am I going to use an AC motor of what voltage, or I would use a DC motor? In that case I'll have to put a rectifier or a DC power supply for my DC motor if I have only AC supply available. Now that will cost some money and so on. So I'll have to look at those alternatives. We assume that we have chosen, or somebody has chosen, to use a DC motor. Of course, again, DC motor is not enough, because DC motors again come in various classes. A simple classification is between what are called series motors and shunt motors. What is the difference between a series motor and a shunt motor? In electric locomotives such as those operating in a city like Mumbai, the motors which are used to drive the wheels are DC motors with a series connection, whereas in many industrial applications the motors will be DC motors with a shunt connection, or even with what is called a separate excitation. So what is the difference between a series and a shunt connection? As the word series suggests, in the case of a series motor, the armature is connected in series with the field winding. That is, the same current flows through both the windings, the armature winding as well as the field winding. Whereas in the case of the shunt motor, as was shown in the diagram earlier, here is the diagram once again. In the case of a shunt motor, the two currents will be different. Armature current will not be equal to the field current, and in fact they may come from two different power supplies. For example, one way is to connect the field winding to a DC voltage source which is kept constant. You don't change the voltage of the DC supply. Such a scheme is known as a separately excited DC motor. Separately excited because the excitation, the power source that produces the current in the field winding, is separate from the power source that produces the armature current. So we have a separately excited DC motor here. And as you can see, in the case of the separately excited DC motor, the field winding is connected to some power supply. Hopefully that power supply voltage will remain constant, and therefore the field current will remain constant. So although I have shown it here as a function of time, IF as a function of time, in this particular application it will happen that IF is actually a constant, maybe 2 amperes or 5 amperes or whatever, and hopefully the field current will remain constant at that value. We may not make any provision for changing the value of the field current, or for making sure that the field current remains constant at that value. One simple way in which the field current, one can provide for the field current to remain constant in spite of changes taking place in the power supply voltage is, of course, the following simple connection. You have the field winding, but in series with it you connect a resistance or a resistor whose resistance is Rf, R for resistance, F for field circuit resistance. And the arrow here, what is it supposed to tell you? That this resistance can be varied, or this resistance can be changed. Changed how? Perhaps by an operator. And this series combination is then given to some power supply voltage, let's say EF, E for EMF or voltage, F for field, and this produces the field current in the field circuit or in the field winding. And an operator who is watching the whole thing may find out what the field current actually is at any moment of time. So there may be an ammeter connected here in the circuit to show the field current, and on the ammeter dial there may be a red mark to show the desired value of the field current. And so here is the operator who is sitting there, and if the field current value deviates from that specified value, the pointer on the ammeter is not against the red mark, then the operator will intervene and adjust the resistance, either decrease it or increase it as the case may be, so that the field current is kept at chosen or specified constant value. Now here we are assuming that the field current is kept constant, and we are not worried as to how the field current is kept constant. In other words, whether it is done automatically or by a man, whether the control for the field current is manual or automatic, or the adjustment, we are not going to look at that at the moment. So we will simply assume that the field current will remain constant at some pre-calculated or specified value IF. So we have chosen that we will use a DC motor, and we will use it in the separately excited way, keeping a constant field current IF. Now the load, the grinding wheel it may be, or it could be a lathe which is connected through some belting to the same motor, and so on. These different devices may require different speeds of operation and may require different torques. So my motor, depending on the particular application, will have to produce a specified torque at a specified speed. So this is something which begins the specification of the control system. We can't simply say motor, DC motor, I am going to use it in the separately excited fashion, because as you know, electric devices have associated with them power, electric power. So in this case, it's not enough to say give me a 230 volts DC motor. You have to say what power. So depending on the various loads that the motor is expected to drive, the torques and the speeds at which the load has to be driven, one can calculate the power that will be used up by the load. This is called the mechanical power. So P load, load power, and that, as you know from mechanics, is the product of the torque TL and the angular speed omega L. So the power that is said to be delivered to the load, which is consumed by the load ultimately, for example, there is grinding going on, so there is friction, there will be heat produced, some job is being turned, once again there is friction, heat will be produced in addition to motion, and so on. The load power PL is given by TL into WL. Check that this formula is correct by looking at the units and the dimensions of the quantities that are involved. What is the dimension for angular speed omega L? Although on the shop floor one will talk in terms of the RPM speed, the speed in revolutions per minute, because that's a convenient thing to talk about and think about. Although I'm sure you don't really have a very good idea of what's the difference between, say, 500 RPM and 1500 RPM, except that 1500 RPM is faster than 500 and sort of 3 times as fast. But we really have no feeling about how fast is 1500 RPM. But anyway, the speed on the shop floor will usually be specified as revolutions per minute. So one may say that this particular load is to be driven at 1500 RPM, 1500 revolutions per minute. But for theoretical work, the preferred unit is not RPM but is radians per second. Why? Because the second is the unit of time, at least in physics, and the radian is the unit of angle in many applications rather than degree. This combined unit, radians per second, radian is supposed to be dimensionless, second of course has the dimension of time, is sometimes referred to as Nepper after Napier, but one may use just the expression radians per second. So the angular speed omega L is in radians per second. What about torque? Well, what is torque? Torque is nothing but moment of a force, or the moment produced by two forces, as one says, moment of a couple. So torque is force into distance. You can think of a torque being produced by a force being applied at a particular lever arm length. So torque is force into distance. So we have force into distance, then we have multiplied by radians per second. Force, of course, what is the unit for force? The unit for force is a Newton, and you should recollect the definition of Newton, the unit of force, the, what is it called? The International Standard System of Units. The Newton is the unit of force. For distance, the unit will be meter, so the unit for torque will be Newton meters. This gets multiplied by the angular speed, which is per second. So you have Newton meters per second, or Newton into meters per second, and that has the same dimensions as power. Of course, mechanical power by definition is this product, torque into angular speed. So when you think of the load and the application, the thing that has to be specified for somebody to select the motor and then to build the control system and so on is what is the requirement. What are the requirements of load power, load angular velocity or speed, and therefore load torque. So in a particular application you may say that we require a torque of so many Newton meters at an angular speed of, let's say, 1500 RPM, or so many radians per second. Now of course, as you know, mechanical power at an earlier era used to be specified as so many horsepower units, or HP, and in some shop floor establishments you may still find the unit horsepower being used. So you may say that the load requires 5 horsepower. As a result, you will use a motor which is capable of producing more than that. But today, of course, the unit of power is not horsepower, but it is a watt, named after James Watt. watt, or it could be a kilowatt. A practical unit of power will be a kilowatt, and you should know the conversion relationship between horsepower and kilowatt, just in case you are faced with specification of the motor in terms of horsepower, power specification in terms of horsepower rather than in terms of kilowatts. So we may even speak of the load power requirement in terms of kilowatts, and we may say the load consumes power at the rate of say 5 kilowatts, and the load has to be driven at a speed of 1500 rpm. So naturally now the motor that I have to choose has to be such that it can deliver power of, in fact, more than 5 kilowatt at a speed of 1500 rpm, and perhaps even a higher speed if it may be required. So accordingly then one will choose a motor. So one will say we want a DC motor of about say 6 kilowatt and 1500 rpm. You may not have a motor available exactly with these specifications, so you choose something which is commercially available, which fits the requirement as closely as possible. If 5 kilowatts are required, you don't want to use a motor which can produce up to 10 kilowatts. The motor will be bigger and you will not be using its full capacity. Whereas you would not use a motor which is supposed to produce 5 kilowatts, because that may be just enough. Similarly, the speed. If the motor runs at a lower speed, then you will have to use gearing arrangement between the motor and the load to produce the desired speed. So one chooses a motor which fits the specifications of the load. Alright, so here is the load, 5 kilowatts at 1500 rpm, and then we have chosen a motor which will produce more than 5 kilowatt but not much more, and will run at 1500 rpm and maybe even at a higher speed. And now I am going to connect the motor to the load, and I am going to control the load not directly by cranking the handle but by controlling the motor. So now I have to devise a system with which I can control the motor. The aim is still to control the load. The aim is not to control the motor. I am not interested in just making the motor run. The motor has to drive a load. What motor I have chosen has depended on what load is given to me. But instead of worrying about the load all the time, now we should worry more about the motor and how to control the motor. I said that I already assumed that the field current will be kept constant. Now suppose the load torque requirement changes or the load speed requirement changes. Right now it's a grinding wheel, but then I may disconnect it, remove it from the shaft and put on the shaft something else which requires a somewhat different power and a somewhat different speed. Now of course if the new application requires a speed which is much higher than the speed for which I chose the motor, 1500 rpm, then it may not be possible to do it very easily. As I said, one may have to introduce a gear train. In fact, something like this happens in an automobile. As you know, in an automobile and even in a scooter, one uses the gear mechanism and one shifts or changes the gear. So what's happening there? What's happening is that you have one shaft and you have another shaft. They don't run at the same speed and they don't transmit the same amount of torque. and you have gear wheels on the two shafts, and depending on the ratio of the teeth on the gear wheels, the speeds and the torques have a certain ratio, and by changing these gear wheels you can change the torque ratio and the speed ratio. So one may install such a mechanism so that starting from as high a speed as 1500, I may be able to get lower speeds by going into a lower drive or a lower gear, shifting into a lower gear. And of course, because my motor can still produce 5 kilowatts, if the speed is lower, then I can produce a higher torque. And this is exactly why you change gears when riding a scooter or an automobile. To start the motor, or to make it go, or when going uphill, you require more torque, so you shift into lower gear. Whereas once the motor has acquired, I am talking about the automobile car, motor car, once it has acquired enough speed, then not much torque is required, just enough to overcome friction and whatever little unevenness may be there on the road. So you require much less power. However, the IC engine, the engine which is the source, prefers to run at more or less a constant speed. That's one of the features of a petrol engine or a diesel engine. It's not that it has to run at a constant speed or it will run at a constant speed, but varying the engine speed itself directly is much more difficult. So we'll have the engine which is going to run at more or less the same speed, but the drive shaft or the car speed is going to change, and this you achieve with the help of the gear train or the gearbox of the motor car or of the scooter. But it may be the case that you don't have a gear train, and therefore you may have to operate a load at a lower speed than the 1500 rpm, and perhaps with a greater torque. It may not be possible to produce more power than what the motor is designed to do. As I said, if it's a 5 kilowatt motor, then you don't expect out of it 10 kilowatts. It will just not produce that power. The winding may get overheated if you try to draw more current and things like that. So maybe with the same power requirement, however, or with lesser power requirement, you could operate a load at a lower speed. So your application may be such that what is required is only a constant speed. I am only going to use the motor to drive a grinding wheel, and the speed of the grinding wheel is going to be kept constant. In fact, it may be higher than 1500 rpm. So such a drive is obviously going to be called a constant speed drive. The object is to keep the speed constant. So as the grinding wheel does its job, depending on the surface which is being ground, the amount of torque required may change, but I may want the grinding speed to remain constant. So this will remind you of what we talked about earlier, trying to keep something constant irrespective of or in the face of something else, disturbances. In this case, change in the load, nature of the load itself, the material which is to be ground, to the surface which is to be ground, depending on its nature. If the grinding speed is kept the same, the torque that is required may be different. Of course, the amount of material which you want to remove by grinding, so the depth also can be different. But we want constant speed. So we want that the wheel should run at a constant speed irrespective of the torque changes, the load torque changes that may take place as the grinding job proceeds. So here is one application: use a DC motor to provide a constant speed drive. And in fact, we will see that a DC motor, a separately excited DC motor, comes very close to being a constant speed drive, but unfortunately not 100% constant speed drive, as we will see. But in many applications, one may just put a motor there separately excited DC motor. Of course, you have to make arrangements for starting it properly and whatnot. So there are cares to be taken in that regard. But by its very nature, as we will see when we write down some equations very soon, the DC motor speed will remain very nearly constant. And if that very nearly is acceptable for your application, that's good. Then you don't need to do anything more. Then what is the control system going to be? Nothing much except turn on the motor and turn off the motor when it is required and when it is not required. Of course, make sure that the field current remains constant, and if that also the power supply is fairly reliable, no need to worry, field current will remain constant and the motor speed will remain nearly constant. But this nearly may not be good enough. It may remain constant within, say, plus minus 5%, but a job may require the speed to remain constant within 1%. This we referred to earlier as regulation. So if the job requires a regulation that is better, that is the percentage variation is less than what the motor will do on its own, then you have to do something. The speed control system cannot be simply turn the motor on, taking care of the starting current and whatnot, and that's it. But there may be applications where the speed is not to be necessarily kept constant, but to be changed from one job requirement to another, or as things happen on the same job, the load torque and the speed therefore may go on changing, the power requirement may go on changing, and so such drives are referred to as variable speed drives. Now DC separately excited motor, DC motor by itself is not going to make a variable speed drive if there is nothing else there, but the armature connected to the DC power supply, the field winding connected to another DC power supply, and both the power supply voltages have been kept constant, reasonably constant, then the thing is not going to behave as a variable speed drive. It can provide torque which varies, but it will not provide you speed which can vary. But in some applications the speed may have to vary right from 0 or very close to 0, a very slow speed, to what may be called the full speed. And at one time you may want the motor to operate at 100 rpm, at another time you may want to operate it or want it to operate at 1000 rpm. So such a thing is called a variable speed drive. Now if you want to use a separately excited DC motor for this purpose, then you have to do something more than what we have thought of, and therefore the control system design problem is not over yet. We have to put some more things, and we have to see how they can be adjusted or controlled so that the speed can be changed as and when it is required. Of course, today one may find that instead of DC motors, one may prefer to use AC motors, and that one of the reasons, of course, is that what is available to you as power supply is not DC but AC. So AC requires rectification to DC and then use the DC motor. This is still going on in the suburban railway system of Mumbai. So there are rectifiers, and then there are the DC series motors under the coaches. But one may prefer to use an induction motor. Then it's a different problem altogether, because now we'll be looking at an induction motor rather than a DC motor as the prime mover or as the actuator for the load. And so one will have to look at different considerations altogether. For the moment, let's assume that we stick to a separately excited DC motor, but I want it to run at different speeds depending on the applications, and perhaps produce different amount of torques too. How shall I do it? Now, when one tries to do something like this, get into design, you need to know something about the motor. I first put down some crude calculations, 5 kilowatts, 1500 rpm, you can calculate the load torque that will be produced. But one will require something more than that. I'll have to relate the torque which is produced by the motor shaft, that is because of the interaction between the field or the flux and the armature current. I'll have to find out how it depends upon the armature current and also on the flux phi. Now this is where we enter the area of what is called modeling. It's a very fashionable word. Of course, I am not referring to modeling in the commercial sense of that term. I am referring to modeling of engineering or physical systems. What do we mean by modeling in this case? Of course, modeling or models can be of different types. One of the earlier ideas in connection with modeling was what is called a scaled down model. Instead of a big motor, I may have a small motor, much smaller motor. In fact, such modeling is done even today. As a sport or as a hobby, one talks about aero modeling. Since perhaps you cannot buy and fly a big aircraft, you make a model of it which has a small engine driving its propeller, and then you play with this model. Now for that scaled down model to actually fly, it has to be made carefully, and there is a relationship between the aircraft that actually flies in the air commercially and this model that will fly only up to a smaller height and over smaller distances and at much lower speeds. But there are many things which are similar. For example, the wing, both of them require a wing, both of them require thrust. This one has a propeller, the other one may have a jet engine, but thrust is required, wing is required to control it, to make it go up and come down and turn and so on. It requires control surfaces. So there are lots of similarities between that big aircraft and this small one. So this is based on the idea of similarity, and the similarity is a physical similarity. The model aircraft looks like the bigger one, and in fact it has a wing that is like the wing, though not exactly in size of course, but not necessarily even with the same proportions as the wing of the bigger aircraft. But physically it's the same kind of thing. This model aircraft is also going to fly in air as the bigger aircraft does. So this uses the concept of similarity. There are similar laws in operation. The laws of aerodynamics are to be used for both the big aircraft and the small aircraft. And in fact, one may make studies of these smaller models in wind tunnels. For example, wings or wing sections, new designs may be tested in a wind tunnel, and therefore the actual wing that is studied may be much smaller than the wing of the aircraft for which it is being designed. So such modeling still plays a very important role, and it is based on knowledge of the underlying physics or the laws governing the phenomenon. In the case of aero modeling, the laws of aerodynamics. Now in a similar way, you may have a big motor, 5 kilowatt motor, and you may have a much smaller motor, what used to be called at one time fractional horsepower motors. These were not for fun, but for small jobs. For example, a mixer will require much smaller power, although it may require higher speed, a few watts perhaps. The motor will be much smaller, but again it will be governed by the same principle. This motor, like the other motor, will have windings, and one will talk about voltages, currents, and since it's an electric or electromagnetic motor, one will talk about magnetic flux or field and things like that. So the physics or the laws that are used will be similar. So this is modeling based on similarity or scaled down model. There is another sense in which the expression model is used, which again was being done quite extensively in the Second World War and period immediately following the Second World War. Nowadays one does not find those things, but some of you may have heard of analog computers. You can spell it in two different ways, analog computers. I have seen and worked on an analog computer setup many years ago, and they were quite interesting things to work on. Today you can build or make an analog computer or an analog computer system by simply using, what is this a symbol of? An operational amplifier. So by using a number of operational amplifiers along with resistors and capacitors, you can build an analog computer system which could be a model of something else. For example, there may be a mechanical system consisting of what is called a mass, a spring, and a dashpot being activated by some force. So you have a purely mechanical system, and the variables of interest or relevance are mechanical variables: position, velocity, acceleration, force. The parameters that one talks about are mechanical: mass, stiffness of the spring, the coefficient of friction or viscosity of the dashpot. So something mechanical. So here is a mechanical system. On the other hand, the analog computer system or setup will consist of purely electrical or electronic devices, and what you can talk about there are usually only currents and voltages. In the case of an analog computer setup, it will be really voltages that one will talk about. Now, in what sense can the analog computer setup be a model of the mechanical system? It is a model in the sense it is an analog of the mechanical system. So you talk about an electronic or a analog computer setup which will model a mechanical system. So this is not like the natural, the similarity modeling based on similarity. The op-amp based system is not anyway like the mass spring dashpot system. It's made up of totally different things. Then what do we mean by analog? What we mean by analog is that one can set up a correspondence between the variables in one case and the variables in the other case. In the mechanical system, the variables are position or displacement, velocity, acceleration, force, torque, and whatnot. In the case of the electrical or electronic system, the variables will be mostly voltages, outputs of the various op amps in your op amp circuit. But you can set up the analog computer system, that is the op amp circuit, choose the resistor, capacitor values in such a way that there is a correspondence between the voltages, output voltages of the several op amps, and between the various mechanical variables like position and velocity of the mechanical system. and usually this is done through the help of equations. It is possible to do such analog modeling without worrying too much about equations. For example, one can even have a more primitive model of the mass spring dashpot system, and I will draw the circuit diagram. Here it is, a resistor in series with an inductor in series with a capacitor connected to a voltage source, or what we refer to as a RLC series circuit. In this one, of course, what can we talk about? We can talk about various voltages, source voltage, resistor voltage, etc. And in this case, because it's a series circuit, only one current, namely the current in the circuit. So these are electrical variables or electrical quantities, current and 3 or 4 voltages. In the case of the mass spring dashpot system acted upon by an external force, you have various positions, velocities and forces. Now one is said to be an analog of the other, or an analog model or a model of the other. The RLC series circuit can be used as a model or to model the mass spring dashpot system. And one way of doing it, seeing that it's a model, is by writing down the set of equations that govern the behavior of each one. And this is an exercise which you should carry out. So this will be a home assignment for you. As electrical engineers, of course, you are familiar with RLC and even more sophisticated electric circuits, but you should also have some feeling for simple mechanical systems or components like the mass, the spring and the dashpot. Write down the equations for the electrical circuit, write down the equations for the mechanical system, and then see for yourself if there is some correspondence, some resemblance, some similarity between the two. I am saying one should use the word correspondence rather than similarity, because the symbol V in electrical engineering will denote voltage, whereas the symbol V for a mechanical engineer will denote most probably velocity. The current is denoted by I, whereas the force is denoted by the symbol F, small f or capital F. So it's not similarity or resemblance in that crude sense that the same symbols or letters are used, but the equations, there is a correspondence between them. I would like you to go through this and be able to see that, okay, the source voltage here V corresponds to what? Does it correspond to the force in the other case, or it does not? The current in the circuit, what does it correspond to? Does it correspond to the position of the mass or the position of one or the other end of the spring? Of course, we will assume that the mass is a point mass, so it is specified by only one coordinate, x coordinate, but the spring of course is extended, so x1 is the position of the mass to which one end of the spring is connected, x2 is the other end of the spring, and so the spring will have a length x1 minus x2 or x2 minus x1 depending on which way the coordinate axes are, and depending on whether this is less than or greater than the natural length, the free length of the spring will be in compression or in tension, and therefore will produce, or it's being affected by a force of compression or a force of tension. Similarly, the dashpot, one end of it is fixed, the other end of it is connected to the spring, so the plunger of the dashpot moves, therefore one can talk about its velocity, and so on. Now in order to do this, of course, what one does is, first one looks at the components of the two systems. In the electrical circuit case, the components are simply the resistor, the inductor, the capacitor, and the voltage source. For the mechanical system, the components are the mass, spring, dashpot, the support to which the mass and the dashpot are fixed, and the driving force or the displacement source, as sometimes it may be thought of. That is, rather than force, you produce a motion of the mass and then see what happens. So the system is built out of components, and one may start by writing equations for the components first, and then looking at the equations together or combining them to get the equations for the system. So do it for the RLC series circuit. Start at the very basic level, start with each one of the components, resistor, inductor, capacitor, voltage source. Write down the equations that describe only the component, each component separately. Write down an equation that describes only the resistor, an equation that describes the behavior of the resistor under normal conditions. What is that equation? It is simply as simple a thing as the voltage of the resistor is the resistance R into the current of the resistor, V equal to Ri, Ohm's law, statement of Ohm's law. That's the equation for the resistor, V equal to Ri. Similarly, there are equations for the inductor, for the capacitor, for the source, voltage source. Write down those equations. But that's not all. You just don't have the resistor, inductor, capacitor, and the source. They are connected together in a particular way, which is called a series circuit. Now this particular way of connecting them together in a series circuit is associated with some more equations. So it's not just the equations for the four components, but you have some more equations. What are they in this case? The components are said to be connected in series. So what does that remind you of? It reminds you of two laws or rules which are named after Kirchhoff. Notice the spelling of the word or of the name. You may not know who he was or when he worked or what did he do, but the least courtesy you can do to him is to spell his name correctly. Kirchhoff with two H's. Don't call him Kirchhoff, or don't write a single H where there is a double H, and there is a double F also at the end. Of course, as the name suggests, he was a German or worked in that part of the world. So there are these two laws or ways of writing equations that are named after Kirchhoff. Kirchhoff's current law and Kirchhoff's voltage law. Using these two then, and using the component equations, one can write down a set of equations for the RLC source series circuit. For the mechanical system, again there are similar laws. For the mass, what is the law? This law of course goes back to Newton, and it simply says the force is mass times the acceleration, or mass multiplied by the second derivative of the position or displacement. So that's Newton's law. For just a point mass or a particle of mass m, F equal to ma. What are the laws or what are the equations for the other two components, the spring and the dashpot? Then these three and the supports at the two ends are not just there, they are connected together in some particular way, and there are laws involved here. Although they don't have any particular names associated with these laws are nevertheless involved. One may, of course, if a mechanical engineer is given this problem, he will at once write down the equation for the whole system, but as an electrical engineer it may take you some time to write down a number of equations and then from them obtain maybe one single equation that describes the mass spring dashpot system. So write down this for the mechanical system, go through the fundamental steps, component equations, equations that arise out of the interconnection, then from them get some equations. Then on the one side you will have the circuit equation or equations, on the other side you will have the mechanical system equations, and now see for yourself if there is some correspondence or if there is some resemblance or similarity. And therefore you could say that the RLC source series circuit is a model of the mechanical system, or you may even think of it the other way, the mechanical system is a non-electrical model of the electrical system. This is a second use of the word model. So do carry out this home assignment.